cloud. If you have Jupyter installed, you can just run it locally, and it's faster and better because you don't have to wait for their free servers to decide to let you in. So, right quick, I'm trying to figure out like where everyone's kind of coming from. So, who has used any sort of symbolic computing before?
Symbolic.
Or computer algebra systems, what they're also known as. Who has used one and doesn't know it is the other question. Like, I see a lot of people. Has anyone used Mathway?
Oh yeah.
Yeah.
Or is Symbolic? Oh, Symbolic.
Oh, what's that one?
Symbolic.
Oh, I'll go with help if I the home row. Symbol lab or symbol?
Yeah, that's all got the calculus.
Oh, okay. I never heard about this one.
It's really good. Yeah. Elite. Wolfram.
Yeah. Like who's used like Wolframalpha?
Yeah.
So like all of these are, symbolic computing because like insert cell below. If you have like x equals 5, and y equals x plus 3. Y is going to be 8, but if you like change x, it's not going to change y. So like most, computer systems just working like with literal, discrete values, not actually working like, here you can just say like integrate x squared, and Wolfram or any of the other ones can figure it out. So pretty much, if you want to follow along, the easiest thing to do is if you go to Finder, you can give it any Jupyter notebook, which in this case, you probably want to give it up here. I've got all of mine in this GitHub repository. So it'll load up and actually let you run Python sort of online. And then who's used Jupyter notebooks before? Does anyone like haven't heard of these? Not too familiar? So the idea is that like, this is Python, so programming language. But instead of having like, a program and you run it through like the terminal, instead it's kind of like, it's like half blog posts, half programming language. So any place where you see there's like, words, you can just create whatever you want. And then any place where there's like a box here, if you hit like Shift Enter or click, it'll actually run the code in that section. So I like it because it's kind of a good compromise between, when I'm just like programming and coming up with stuff in like the interactive mode in Python. But at the end of the day, like if I close my interactive session, it's all gone. Versus like if I open up like my compiler and everything, and I have to like make all these files, it's like there's a lot of setup. So this is like a good kind of, you can just sort of like think as you go and everything. So is anyone else going to try it on Finder?
I got it to work on.
You got it to work.
So yeah.
So if anyone has any questions about how to make that happen, see it over there. Otherwise, it's a peanut. So right quick, like what is symbolic computing like useful for? That's the question. Yeah.
Not problems like hamburger?
Yes. That I think is one of the biggest use cases. So we'll talk about like how to do your calculus homework in a bit. So I think the first thing that I want to talk about is like, let's take like, you got this ideal gas law, right? PV, nRT, and that one's like not hard, because it's all just algebra. So like you might go on WeatherSign and they'd say that like if you have a pressure of 1 atmosphere and a temperature of 300 Kelvin and you have like 1 mole of gas, figure out what is the volume, right? And you can go in and, do the algebra and solve it. But I think because this one's sort of simple, it's like a good example of how to get started with using Sympy. So what I've done here is Sympy is a package for Python that does symbolic computing. So similar to like Mathway or Symbolic or Wolframalpha, this is one that's open source that works through Python. So I think the good things there is like all your Python skills you can just like bring into play. Whereas if you want to use Mathematica, like 1, it's not free, and 2, you have to learn Mathematica. Mathematica might be a little better, but this has some, the advantage of being free and easier to use. So if you look at the first line here, one of the big things is like when using Sympy, you actually have to define your variables a little bit differently. So this is letting Python know that these variables aren't just like holding some value. It's actually standing in for this object, which is like keeping track of it in sort of an algebra way. So like if later you go and change the value of p, it'll then sort of like recalculate all the formulas that p is in, because it knows that like it's not just that p is 1, p is like a variable that could be anything. So once you define these, then you can essentially make an equation. And the other thing is like if you, for a lot of functions, you have to be careful. There's a whole thing up here, a page on like gotchas to watch out for, because like if I say, PV equals nRT, that's like a syntax error because it doesn't know what those are. Or even if I put in the multiplication signs, it's still going to be confused because like, that's not a valid left-hand side for an equation. So if you want to type in an actual equation to be like something equal to something else, Sympy has functions for all these kind of basic math things like equals, plus, all that. And it's also nice because it displays equations in sort of a fancy way. It does reorder them based on like the hash values of the symbols you use, so it's still equivalent. So this last part, let's go through this sort of like step by step here. So if I wanted to actually use this to solve like this problem, the main thing that I want to do is I want to tell Sympy that for the value of p, I want to put in the number 1. I also want to tell Sympy that I know how to spell, which it just went away. And then like, let's see, volume is what I'm looking for. So let's say temperature is 300. So this is the sort of thing where you can just sort of go step by step, putting in literal values for the symbolic values. And who here has like seen function calls where you like chain a bunch of subcalls like this? Is this something that's like seen before? Not too much. So right quick, because like it comes up a lot in like stuff that's very object oriented. Python has a function called type, which will just tell you like what is the type of this variable. So this is Sympy core relational equality. So it's saying that it's just some formula with an equal sign in it. So that's actually like an object, if you take object-oriented programming. And because it's an object, it has a ton of member functions, which if you hit dot and tab, you can start to see it'll like list out some of them. And one of those member functions is substitute in. So you can substitute in the value of, say like for t, put in 300. And if you run that, this function then returns like a new object. So it's like a separate equation that it's made, which you can even like hold as a variable. And it is just the same equation you had before, but you put 300 in for t. And if you look, the type of equation 2 is the same type that we had before. So instead of saying like, equation 2 equals, and then you substitute it in, and equation 3 equals, and then you substitute it in, because each of them returns a variable that's the same type as what you had before, you can just string it all the way out. And it's sort of like operating kind of the same thing again and again. So if we wanted to put all the values in, we could say, copy, get rid of all this. Ideally, we messed up. And then define actual literal value for R. Has anyone done chemistry? Does anyone know what I've done wrong here? R is not an atmosphere is for 8.31 room. Which is also an important thing to think about. Like when you're working with numbers, like a floating point doesn't have units. So like if you tell Python to do like, you know, if you travel for 10 miles per hour for 30 seconds, and you tell Python to do that, it's going to say, oh, you've gone 300 miles. So tracking in units is something that's important to do. I think there are even other libraries that will do it for you, but for me, I'm just like labeling all my variables or like being consistent to keep everything in the same system. So like here, this that we put in, what this has done is it's just put in these numbers for this equation. But you can see the equation still isn't that helpful because it just tells you that 2 equals about 83 times t. So what we want to do is have Sympy be able to solve this equation for, you tell it what equation you want it to do, and then what do you want to solve for. So here, it solved this equation for the value t. And something to keep in mind is, if you look at what type that it returns, it's giving you a list. Which does anyone think, like, why would the solve function give you a list? So what if I had it x equals, and symbols, let's say x squared minus 3 times x plus 7, solve that for x. Like, what is this going to give me?
That's an X error.
That is something tricky. The caret in Python is like bitwise XOR. The double asterisks is x squared is x star star 2. Alright, what else have I done wrong? Nothing. Okay. So like it's given me 2 solutions, right? Because you know quadratic equations have 2 solutions. So it's just set up in general that even for an equation that obviously only has 1 solution, it still gives you a list. It's just a list that's 1 item long. And something else to look, because I just chose this polynomial at random. Like what does this I part mean?
Imaginary.
Right. So like it wouldn't normally have any real solutions, but fortunately Sympy, it works with imaginary numbers just as good as real numbers, and it sorted that one out. So what I can say now is I want to solve the ideal gas equation for t, and because I know that there's only 1 solution, I want to take the first element in that list, and then what I can do is then substitute in all the values from whatever problem I have, and there it is. So that's kind of the idea. And any questions so far? It's all super easy. I don't know like how fast to go. I don't know if this is like.
No, it's a good fix.
Okay. So that was kind of a simple one, but that's sort of the idea that you can create variables that like represent the equations you're working with. You can then use different Sympy functions to kind of manipulate those equations. And then you can also, when you're done, if you want it to stop being symbolic and actually do math for you like a calculator, you can just put in what values you have and it will give you the answer. So something that's maybe a bit less trivial is like calculus. Because like, you know, I'm sure you don't need Python to say like, oh, divide by n, divide by r, you solve for t. It's not too difficult, but sometimes they give these integrals which are like, who knows where that came from. So something practically as well, there's this thing called Sympy Gamma, where it's like Sympy, but it's like hosted kind of like free on the web, and you can just type it in, same like Wolframalpha. And I thought it was interesting because it even gives you like step-by-step integrals. So like, does anyone have like a hard integral? Sine of x. That sounds terrifying. I wouldn't want to do that one. Let's see what it says. First thing it says is it's slower than Wolframalpha. There we go. So it looks bad, But the good part is, you're not doing any of this work. Some server out in wherever Sympy lives is. And so you can see that it is taking forever. And brief aside, does anyone have any ideas why it is taking forever to do this one? How does it even do integrals? Answer is that if you go on Wikipedia, it'll tell you that there's an algorithm. And then it makes this nice, here it is. It makes this nice illusion that it takes over 100 pages to describe. So to be honest, I do not actually know how it is doing integrals. That is apparently very fancy and has a lot to do with rational functions. But something to keep in mind, I just gave up. That one was too hard. Is like, does anyone know what is the integral of e to the negative x squared dx? No. This is kind of a trick question, so if you know what the answer is then.
Is it just e to the negative x squared?
No, it's actually, there is no elementary function that you can have that is this integral. So the answer is pretty much there is no answer. So there are some integrals that essentially don't have answers. So one thing that's hard to tell when using like a symbolic computation library is, did it give up because this happens to be one of those integrals that just doesn't have an answer, or did it give up because you know, you're getting a server time for free and they're like not going to give you that much time? So if you run it in your own machine, you can let it run as long as you want. But another side of computability, has anyone heard of the halting problem? So have you heard that there are problems that computers can't solve, even given like sort of an infinite amount of time? So one thing that's kind of interesting is like doing these integral problems. There are some integrals out there that the computer could just never find the answer to. It's like mathematically proven that it's impossible to find that algorithm. And not only that, it's impossible for it to even tell you the difference between not finding an answer because it's lazy and not finding an answer because it doesn't exist. Because pretty much the computer can like look for a day, and then if you hit, you know, Alt F4, Control C to stop it, maybe it would have found it tomorrow. But if it's looking for the one that never has an answer, those never know. You know, maybe 100 days in it would have found it. Maybe not. So that's something to keep in mind when like using this. But then, ideally, all the integrals they give you on WebAssign are purposefully chosen so as not to be one of the infinite set of impossible integrals. And if they do, that would be pretty funny. So, right quick, so I'm declaring the variable x, which remember you have to do it in kind of that special way. And then the other thing is like, you can just assign equations, same way as like variables. So now like f is, you know, this, I should say print. So something that happens is whatever like the last thing to evaluate one of these boxes is automatically gets printed. So if you want to print like more than one thing, you do have to be like explicit with your print statements. But here like f is now like an object, you know, in memory representing this equation, and it can print it out. And then for integration, for the most part, it is just that simple. Integrate, what do you want to integrate, what variable to integrate with, display it, and you know, you can see it looks right. So something a bit more complicated. Who's done solids of rotation? Is that, you doing that one?
Not currently. I did that in AP Calc or AP Calc back in high school.
Oh, okay. What calc does that come up in?
Calc 2, right?
2 usually?
Oh, like the washer method, the disk rotation?
Yeah,
Oh.
all that kind of stuff. The disk method. So like, you know, so something like that gets a little more complicated, and as I get slightly lazier, the argument for using a symbolic library becomes a bit better. For the other thing is like, sometimes it's good just to like check yourself. You know, like if you got like one try left, you know, maybe you should do it by hand for the test, but like you want to be like certain that you got it right. So like, what if we have some solid where you got the sine function going from 0 to pi, and we're going to spin it around this way. So like, for those of you that haven't heard about this thing, because you've been spared calculus 2, the idea is that when you do an integral of this function, you're finding the area under this curve. And when they talk about solids of rotation, they're saying like, imagine you took this curve and you rotated it around this axis, and everywhere that it kind of passed through, you said was a solid. So this would be like a fishing lure shape. But the idea is that if you have some object, and you essentially like trace the outline the object makes, and then rotate it around, that's how you could describe the exact shape of what this volume is by describing its outline, and then doing some calculus, you go from there. And when we say doing calculus, that's when we come back to Sympy. And so we can say we got our variable x. Our function here is the sine function. And then what's the method with the something squared minus the other one squared? Who's in Calc 2? It's like rings, donuts. What are the two methods again? Washers, discs.
Oh, yeah.
Okay. So like for this one, what it comes down to is if you do the integral from 0 to pi of f squared times pi, and like where that comes from is, you know, the area of a circle is pi r squared, right? So an integral is just doing a bunch of adding. So if you take each of these like little slices, like sliced up this water bottle, each of those little circles and add up the area of every single circle, you get the volume of the overall shape. So that's kind of where it comes from. But then depending what function they give you, like this could be some sort of hard integral. But instead what you could have is, you could say integrate, and then you want to integrate pi, which using this like sim.pi means that sim.pi is going to like have like the notion of pi, and then it's only going to turn that into 3.14 whatever if you want to evaluate it later. So like you can see here at the answer, because it's already done it, it actually puts it in terms of pi, which can be helpful because like even if you could do this on your calculator and maybe it would give you the right answer, you know, to be whatever this is, like 4.5 or something, maybe, you know, in a calculus test or WebAssign, it wants you to use like these symbolic values and not approximate pi. So like not needing to do approximations is another big reason to use symbolic computation. But then all it is pi times f squared, and then this is sort of a fancy bit. We'll get back to that in a second. And then integrate the variable x from 0 to pi, and there it is, that's the answer. Who has seen, this is just kind of a fun Python thing, who's seen this thing before? Has anyone used Python a lot? So the idea is like if I have a, you know, in parentheses in Python, I can make it like a list. So it's kind of like an array, but less, you know, picky about what you do with it. And I have here a different list with like my bounds in it, right? So I can say integrate x from my left bound to my right bound. Because what this is saying is take the first element of that array and the second element of that array and then put it together in one big list. But if you're feeling fancy in Python, using the little like star here says take whatever that list is, spell out the elements explicitly, and then fill it in. So that's kind of a fun thing. Like if you have some function, you know, that has like a, you know, a bunch of arguments that you need to put in, you know, or whatever. Instead, if you have all your arguments in like a list, you can just do that, and it will say take this list of arguments and then put the first element of the list as the first argument of the function, the second element is the second argument of the function, so forth and so on. So whether or not you're just using that to like flex on people or you think it makes it easier to read, that's up to you. I think that it's nice because like having to spell it out like this just is extra kind of code, and to me this makes sense. It's like x and then do x for, you know, this list I said before. So let's see right quick. This one we're doing live. solid rotation. Because the other useful thing about using Python is you can make graphs. So like here, someone is asked on Stack Exchange, which I'll probably post this link. They're like, please help, I have no idea how to program, can you do this for me? And someone was nice enough to say yes. So you can actually plot like the different shapes. So like here you can see that they've like described some shape using a couple of equations. And we'll probably try that later if we have more time, mess around with actually plotting the shape that corresponds as well, even looking at that. So any other questions on what we're doing here? What else could this be? Yeah.
What do you use this for personally?
Personally, that's the next part.
Okay.
That's what I'm going to tell you. What I do. Something like that's a good question. What other questions could you answer with something like this? Like, does anyone have to do Fourier transforms? I guess you're lucky. A little bit.
Yeah.
Okay. How do you do Fourier transforms?
I don't do them manually. I
You
will
don't?
never do them.
Because like you can do them, numerically. So the idea is like in calculus, there's a lot of things that come up where you have some function. You got to turn that function into a harder function, and then you have to do calculus on it. So the same with like Fourier transform. I believe it's what e to the negative I p f dx, integral from negative infinity to infinity. So like you have an integral in terms of like imaginary numbers, but the idea is you took a function, you made it even more complicated, and now you have to do the integral. So that's one other good reason for using something like Sympy, because you can have your function, and then instead of just telling it to integrate, just f, you can have it do, let's see if it actually does it. Negative. Using pressure from before. Okay, it's done it. This one I'm not confident it's right because I just did it right quick, but the idea is like a lot of things come up like that, like having to do Fourier transforms. The thing that I use it for, is anyone going to be taking linear algebra? They always want you to find eigenvectors, and like, this is why they made computers. Not even like joking, like, the reason people made computers is because there's a lot of boring math, and like, for a 2x2 matrix, I'll find the eigenvectors for you, that's good practice. Like 3x3, you're like really pushing it, like I don't have that kind of time. And that comes up a lot in like the classes I'm taking. It's like you gotta find eigenvectors because it comes up in quantum mechanics, it comes up in physics everywhere, electrical engineering, like math, all over the place. So for Sympy, you can just tell it, here's the matrix, what are the eigenvectors? Bam, there it is. So it's found them. It also finds the multiplicity, which is like, is the eigenvector used more than once? And it even tells you the eigenvalue as well. And the thing that I use it for is making the fanciest looking homework ever made. Do I have to register my login approval?
I'll sign you up for some spam emails.
Who uses two-factor authentication? Has anyone not heard of this whole thing? So right quick, if you haven't, the idea is that whenever I log in, it also like messages me on my phone to ask that, yeah, it's really me. So the idea is that if someone like stole my password, I don't know, like the camera, they would also need my password and my phone to get into my account, unless they circumvent the security. So, who has never heard of LaTeX and thinks this is terrifying? Yes. Yes. This business.
Who has heard of it or who hasn't?
Who is not? I'm expecting this is like almost everybody. So LaTeX is.
I've heard of it. I still think it's terrifying.
Oh yeah, it doesn't get better. So this guy, he's like the computer scientist guy, you know, the art of computer programming. He came up with LaTeX because the idea is like, have you ever tried to type an equation in like Microsoft Word or something? It is not great. And this is kind of a better solution. So the idea is that this is my document, and when I hit compile, it actually turns this description of my document into a nice looking PDF. So it's like a whole different thing, you know. It is weird to think that you're gonna like type up an essay and then compile your essay. But that is what LaTeX is. And the reason it does that is because like when you put something in Word, if you had the thing where like you got your, you know, your title and you write something and then you want to put in a picture, and then suddenly like the picture goes to the next page and half your text ends up here, you know, it's kind of a nightmare. So the idea is that LaTeX, you tell it what you want, and then it's sort of programmed to use the best practices for typography and try to fit it in. So the computer will essentially try to put this image someplace reasonable, so that it doesn't split the text, so that it's all lined up. So like the downside is you're not really telling it exactly where to put everything. The upside is if it works, it just figure it out for you. So like what I would do is like if I had a homework assignment that was like question 2, part A, find the eigenvectors of this matrix. What I would do is have it print the LaTeX representation of this matrix. So like A is a variable for this matrix. This function prints out all of this. And like we want to change it right quick, like make this one 0, make this one -5, run it again. This description is like the LaTeX description of that matrix. And what I've actually done to make this presentation is Jupyter Notebooks also can use LaTeX for putting equations. So like if I paste in that description, when I actually have it like render the text, it turns into like a nice looking representation of that matrix. So then, you know, I would have here under question 1, you know, the eigenvectors of, give it the equation, can clearly be seen to be, type it into Sympy, and so eigenvex, so you can see that the eigenvex gives me a bunch of them. Hello? Uh-oh. Have the servers gotten tired of my nonsense? Alright, we'll give it a second to run. But the idea then is that I can have it find those eigenvectors and then just tell it, give me the Sympy, or give me the LaTeX representation for those, and paste that into my homework. So it ends up like looking real fancy here, like we recompile. You know, we'll have this, we'll have the eigenvectors, and then any sort of equations. And then especially like if you're needing to do like something fancy like this, instead of like writing it out step by step, the thing I like is that not only can I get Python to like solve some of it for me, but like there's no copy paste on paper. But for here, instead of having to like write out, you know, a sign of X and then I do each step, I can just like copy paste, recompile. It all looks really fancy. That's what I do. So, any other questions? Well, I'm gonna restart Binder here and hope that it thinks that I'm someone worth giving free computer time to do calculus. Anything y'all think that you would use this sort of thing for? Yeah, which I think that's what I use it for most of the time. Yeah, what kind of homework do you have that you could use this on?
I'm gonna probably use for physics. I have to type my equation if it's online.
Oh, okay. Is anyone in Physics 1 right now? Has anyone done it before? Does anyone still have to do it at some point in the future? But you're in Physics 1.
Oh, okay, so maybe do
Yeah.
physics 2.
Oh, okay. So that was something that, let's see if we can do this. Ah, here we go. So the last bit, I want to bring it together, try to do something complicated. We'll see if it works or not. Oh, here we go. So we have the eigenvectors. I only want the first one. So something you notice, like it just said, sim is not defined. Because I've started a new notebook. I haven't run these cells yet. So like it hasn't even imported the libraries. So that's why it's upset at me that, you know, there's stuff that hasn't been defined yet. So the only thing to be careful there of using Jupyter notebooks is when you start scrolling back and forth, you have to kind of keep track of what variables in scope, or you can always just like clear it all out. So 0 is that one, and then it is, which one is the actual vector? 0, 1, 2. The second thing there, and that looks like a list of vectors that is one element long. So that's a vector. So if I dot LaTeX, give me the LaTeX representation of that, it'll do it. Does anyone know like why are there so many backslashes? What do backslashes do when you like print something? Yeah.
Escape characters?
Right. So the thing is, like, when it does this representation, because it's in code as a string, it actually has to escape all the backslashes. So what I can do is if I just tell it to print what that string is, instead of having to see all the escaped backslashes, it just tells me like what it should look like. And then, you know, copy, go back to my homework. Clearly it seemed to be paste. So Overleaf is like a website that lets you do all this stuff for free. It's got a lot of fancy templates. I actually use, when I'm doing LaTeX, like bash on the command line. You just compile your document on the command line.
Is this a collaborative tool?
Yes.
Okay.
I know people that do use it to collaborate, but I haven't used it with them. But it works pretty well. And the other thing is like tons of science papers, like essentially every physics and math paper is usually written in LaTeX. And you essentially send like this file to, you know, whoever you've done the research for, and they turn it into a PDF and put it in the journal. Or, well, they email you back and say your paper's not good enough. We're not going to put it in the journal. But if they did, they would do that. The other brief aside that LaTeX is good for is if you have a lot of like references, like if you ever have to write one of them essays, you're going to like keep track of your references. LaTeX does it automatically. You can just have a file with everyone's like name in it.
Can you spell it?
LaTeX? Yes. It is spelled like LaTeX, but with capital letters to be fancy. And then if you want to be extra fancy, I think there is a command for it.
Yeah, there is.
Is it's always stylized with, you know, like an A going up, the T going down. So you can tell that, you know, this was a guy that cared about things like typography. He's big into it. Does anyone know what kerning is? Anyone been cursed with that knowledge?
Heard
What is-
spacing?
Yeah, the spacing between the letters. It's the sort of thing that once you know about it, you'll never unsee it when it's done poorly again. But the other big claim to fame has is that LaTeX just looks kind of subtly nicer because like it puts all the letters in like the perfect place. So they put a lot of thought into this. It's also a full programming language for no reason, which is terrifying. Like you can make macros in it, you can do anything. Well, you can't, Stack Exchange can because they read Dominic Smith's book. But I just pretty much copy and paste, use it to type things. So that's that. So all this is what I was working on just before I got here. So let's see if we can figure out how to use it to do something that would be really difficult and annoying to do without symbolic computation, as opposed to something that's like, you know, kind of easy, sort of whatever. So if you're in physics 1, what's the kinematic equation? Who's in physics 1? No one's in my physics 1 class, right? You got what? Y is 1/2 acceleration due to gravity times squared plus the initial velocity in y times the time plus the initial position in y. It's like you have this whole equation that describes if you launch something in the air, you know, how how far does it go? And that's in y, same as for x, but since there's no gravity in the x direction, it's just the how fast you threw it times the time plus where you started at. So between these two equations, this will tell you if you want to graph, something flying through the air. That's exactly what the equations say. And so the question is, if you launch something at say 10 meters per second, it's going to sound like WebAssign here for a second. You launch it at 10 meters per second. So what is the initial at some angle theta? What is your initial x velocity? Because you got theta, this is 10, it's one of the trig ones. It's not tangent.
Cosine, right?
Yeah, cosine is for, so whatever the initial velocity is, cosine theta, and then the initial velocity times its sine theta in the other direction. So if I wanted to go as far as possible, what angle should it be? Because there's some that are obviously wrong. Like theta equals 90. It doesn't really go anywhere. Theta equals 180. Also does not work. It's going to be somewhere in sort of that direction. So this is a question for people that are in calculus. How would you find what angle of theta makes this go the farthest? What kind of problem is that? Limit? I think limit's related because limits are where calculus comes from. But you're trying to find the optimal value of something.
Oh, drive it equals 0.
Right. So for optimization problems, the idea is that you would take the derivative with respect to theta, find where that function is equal to 0, and then solve that. But there's a lot going on. There's a lot of equations, there's a ton of unknowns, and that's exactly where, let's see, insert cell above, something like Sympy comes into actually being helpful. So we can start off with all of our variables, and something that is nice about it is Vy not. If you put it in like this with underscores and the brackets, it'll actually render it, with a subscript in a fancy way. So what we can say is that the total time that it's in the air is undefined. Uh-oh. Can someone save me from myself?
Why?
Why? So we display y. That's this equation we had going on here. And then if we display the total time, that's a spelling test. So essentially what I've told it to do is, if this is its equation in y is going to start at 0, it's going to fly, it's going to hit the ground again. I want to know how long did that take. So I could take physics 1 and solve it, or I could just say to Sympy, this is an equation. I don't know what it is, but I need you to find what is t equal to when we say that v naught y is equal to some other thing times the sine of theta. And it figures it out for me. It says, hey, there's two answers. This is what it is. And so if someone was asking, total time, there's two of them, I could always do the thing, right, where I substitute it in. If WebAssign's after me being hey, how long is it in the air if, v naught is 10 and y naught is 3 or whatever, then I'm just, doing, v naught is 10, y naught is 3. And then it's, it's putting it in. Oh, and then say theta is 0. And it will just, give me the answer. And I just got to put in the right numbers and everything. So actually at this point, I could either go up here and you could watch me get myself into deeper and deeper knots with Sympy. Or I could talk a bit about how one of the other advantages of Python is, where that stack exchange is supposed to go. Matplotlib. Solids rotation. Because I think something that I also use it for a lot is whenever they like ask you to graph something, and I don't want to go out there with like a pen and be like plotting values and trying to connect them. I like really fancy looking plots. And the other thing about using like LaTeX, you just like copy and paste this picture in. So that's a whole other thing about how to use Matplotlib. So at this point I think I'm going to turn it over to everyone. Questions, thoughts?
Can you use Google Colab instead of Binder or whatever it's called?
What is Google Plan?
Or maybe it's Colab.
It's code lab right there.
Colab.
CodeLab?
Collaboratory.
What is, yeah, so tell everyone about this because I haven't seen this thing.
Wait, no, it's
Colab.
It's Colab?
Yeah.
Is it?
Like not
It's
Colab.
COLAB.
Yeah, it's like a.
Oh,
Yeah.
COL?
It's in Google Drive.
I thought it was cool.
Collab.research.google.com.
Wait, first link out of that.
Oh yeah,
It's,
the subscription. It's just another site for Jupyter notebooks.
Oh, really? So you're saying if I put my GitHub in here, it's gonna
I'm not
do
sure.
something?
I've barely used it.
Oh, this just made a blank one, but it does look like. Oh, does look like it's working. So how did you hear about Google Colab?
We're using it in my AI class.
Oh, fun.
Yeah, it's what what Ucf AI uses as well.
Okay, I'm gonna just look into that one. Seems faster in these Google servers. We'll see. But like the main reason that I was using Binder is just because like I don't have the thing to plug my laptop in. What I'm usually doing is just running Jupyter notebooks directly. So something to talk about, if you want to actually use this stuff, one thing you can do is just go on Google, use Google Colab or Binder. Or if you want it locally, what I use is just download this Anaconda thing. It is a huge file. It's not actually downloaded. But the thing is that it's got like all of it in it. So all like the scientific libraries, Sympy, NumPy, plotting, and then Jupyter notebooks as well as a couple of IDEs. And it also just puts Python like on your command line if you were more of a command line person. So that's what I would do next is download Anaconda, and then the next time you have one of these terrible homework problems, try it out in Sympy. And this is, real quick, Matplotlib is the Python library for making these graphs. It does have a lot going on, but if you can see right quick, what I said is, I said X is all the numbers from 0 to 5, not like literally all the numbers, but you know, a good sampling. Because NumPy is doing numeric values, unlike Sympy, which is working symbolically. And then I just said plot X versus the sine of X, and there it is. And so you can incorporate that sort of the same stuff into, you know, like making plots of any of these functions you're working with. And sometimes, like, if I want to know I've done it right, I want to see like a plot to see like what does it actually look like. Or even not just for homework, but like doing, you know, research or something that I've been wondering about. Like, you know, if I'm doing like a engineering project, if you're in like senior design or something you want to test out, I think it's nice that it's all in one place because like I know how to use Python, like I kind of know how to do calculus, I want to make plots. So if I know how to use like Sympy, NumPy, Matplotlib, it's like all there. And all the sort of like skills I have doing programming, I can like transfer those over to math. So I think that's just a the best part, is that like if you have a lot of skills programming, if you know something like this, and like the best thing to do is just like Google it, because like Sympy's documentation, some of it's actually kind of funny, but it's pretty good. And then this will just kind of tell you how do you take like those programming skills and turn them into math skills. All right, any last questions?
For like discrete math, like what kind of diagrams and stuff do you use this for, or is it more specifically like could you make diagrams and whatnot with this?
It could be for anything. If you look, I have a couple of half-finished Jupyter notebooks where I use some of the discrete math stuff. So like, you know, in discrete math class, they're always on like, how many ways are there to put, I don't know, like 3 balls in 7 boxes or something, right? You know, like 7, choose 3. That marker. There's also SciPy, which is like, some of those more specialized functions didn't end up in NumPy, but like they have the choose function. And you could use it to like work with factorials and stuff symbolically. So, yes. What is this? Oh, there's another fun fact about Python. In like C or something, if you're just using a regular integer, that goes up to what? 2 to the 31st, that's a couple billion, right? By default, Python integers are unlimited precision. And so you can see here that, that I actually got a number so big that like a float couldn't hold it anymore. So my idea was if I use Sympy and infinite precision integers, it would give me the answer. The problem is that it very quickly gives up because it will take like a week to run this program. Oh, it's a nice class. But yeah, discrete math works too. Anything else? Yes.
No. Like side related, I guess what's like the longest time you've let one of these things run?
Just for Jupyter Notebook, I get like bored an hour in. For like other research stuff I've done, like I probably wouldn't use a Jupyter Notebook. I don't know how much it impacts the performance to like run that, but I'd probably write like a Python program. I might test it out in Jupyter Notebook, but if I wanted to run for a long time, I'd probably do it through the command line. And I think like doing, the most I've seen is Ucf Harrington. Has anyone heard of this guy?
No?
He does exoplanets research. So they look for planets in other solar systems. But what that means practically is they write Python programs and run them on this really fancy computer. And for those, like finding a new planet from like one orbit takes maybe 2 or 3 days of running the code. And that's for analyzing one data set. So somewhere in the physics building, there is like 50 terabytes of planets sitting around. And if you're interested in this sort of stuff, there is this class. I think it's a great course. I've taken it before. It's kind of like an introduction to Python as well as like using Python for science. So like if you're doing like CS2 or something, you might be kind of past this. But if you're interested in like Python or like the sort of stuff that he does, like how do you use Python to answer like science questions? Like, you know, how do you find a planet in Python? This is like a good course to kind of start that sort of thing. And then, I don't know who actually would want to do this, but even if you're taking a lot of programming, but you're interested in just that sort of thing, astronomical data analysis, it's like all a course done in Python, and it's about like how do you answer like sort of difficult science questions using like data analysis, basically. So the final project for that class, I think, is the funniest homework I've seen, where it takes you through all the steps of finding data from a telescope, analyzing it, looking at the source of errors, correcting for cosmic rays, and then the last line in your homework is prove that dark matter exists. Write an essay about it. And that's when it all comes back to, you're probably doing that essay because you have a lot of math and graphs and stuff in LaTeX. And so you've built up like the sort of Python skills to, you know, do all the analysis and then bring it together into, you know, we are confident that dark matter exists because when we look at galaxies, their spectrum appears a very particular way mathematically, which you've shown via your program, and you've then made an essay about. All right, I'm gonna get pizza. Any other questions, Jason, just talk to me.
Next one, guys, if you put out the feedback form, you can give them to me, to Harka, or you can just leave them up there as well. Yeah, thank you guys so much for coming out.